In Chapter 15, we will be studying carboxylic acids as well as nitriles. The enzyme that is shown here is acetyl-CoA carboxylase. This catalyzes the carboxylation of acetyl-CoA, so we can see the structure of acetyl-CoA on the left, and that's going to add this CO2H group, which gives malonyl-CoA, and this is important in the biosynthesis of fatty acids during catabolism, and that functional group there is a carboxylic acid. Carboxylic acids can be made into several different derivatives, and these compounds that have the C double bond O and some other functional group coming off of that carbonyl are referred to as carboxylic acid derivatives. These are present in a lot of industrial processes and most biological processes. So we'll see these often in DNA synthesis, protein synthesis, fatty acid synthesis, and other metabolism as well. These are the starting materials from which their acyl derivatives are made, and understanding the properties of these reactions is really important to understanding organic chemistry from the biological perspective. So we have acid chlorides, we have esters, amides, thioesters, which have the sulfur here, and then one thing that is also present is our acyl phosphates. So when we start talking about ATP or adenosine triphosphate, we're going to encounter different acyl phosphates. When we name carboxylic acids, which are often abbreviated RCO2H, if they're derived from open-chain alkanes, which is the ones that we'll see most often, the terminal E in an alkane is cut off, and then we substitute that ending with oic acid, and the carboxyl carbon atom is always going to be at 1, just like with aldehydes. So if we have 3 carbons, our alkane parent was propane, we're going to drop the E from propane and end it with oic acid. So this is propanoic acid. 5 carbons is going to be pentanoic acid. We list our substituents as we normally would. So this is 4-methyl pentanoic acid. And we don't need to include the number 1 because for carboxylic acids, it's always at 1. Our substituent here is at 5 of 8. This is 5-tert-butyl octanoic acid. For nitriles, we drop the E of the alkane again, and we end it with O-nitrile, and the nitrile carbon atom is 1. So this one is acetonitrile when it has 2 carbons. That's the common name. The IUPAC name here would be ethanonitrile. So we drop the E from ethane, and then we end it in O-nitrile. This one here is benzonitrile. And if CN is coming off of a ring, we have 2 here. This is 2,2-dimethyl cyclohexane carbonitrile. So if we were to name these, without the alkene would be butanoic acid. We're going to list the methyl first. So this is 3-methyl 2-butanoic acid. Here's my long carbon chain. I have an ethyl at 2, pentanoic acid. And this becomes butanonitrile. Carboxylic acids can form hydrogen bonds, and they show up as dimers. So these have very high boiling points. So we have the carbonyl oxygen here that can hydrogen bond, and those can form these dimers. So acetic acid, which is the carboxylic acid, has the boiling point of 118 degrees, and something with similar molecular mass and in an alcohol is 82. So carboxylic acids have higher boiling points than alcohols do. Carboxylic acids are typically also water insoluble. So if I added some carboxylic acid into water, nothing would happen. It would just kind of float at the top and not dissolve into the solution. But if I added sodium hydroxide to that, this is a base and this is acting as an acid because it is a carboxylic acid. The negative charge here can pull off this proton, just like our acid-base reactions we've done before. This becomes O-, and we get water as well. So we form this carboxylate salt, which is water soluble. So carboxylic acids are generally water insoluble, but if we can make it the carboxylate salt, it becomes water soluble. Carboxylic acids, when we react them with water, can also form these carboxylic acid salts and form H3O+ in the process. And these are relatively strong acids if we compare them to water and ethanol. So ethanol is a weaker acid with a pKa of 16, and if we have a propanoic acid that has a pKa of 4.87, as we add different groups to it, like fluorine groups, that makes it very acidic. So the Ka, remember, is the dissociation of water, and pKa is equivalent to the negative log of carboxylic acid. The general pKa of a carboxylic acid is around 5. And that will change depending on what the R group is. So an alcohol has the pKa of around 16. Phenol is around 10, or 9.89. This carboxylic acid is 4.76, so that's specifically for acetic acid. And then for HCl, it's -7. So HCl is very acidic and ethanol is not so much. So this is our acid strength. And something that makes it a stronger acid is resonance. If we look at ethoxide, which is formed when ethanol loses the proton, so we have this H here will get removed by the base, that forms the ethoxide. So all of that negative charge is on oxygen, whereas with this acetic acid, if this loses hydrogen, we get this carboxylate anion. We can draw a resonance structure so that the negative charge is getting spread out between 3 atoms. Here the negative charge is localized only on the oxygen. So that oxygen has to carry the burden of that negative charge, so it's not going to be as strong of an acid if it can't stabilize that negative charge. If we add different groups to the carboxylic acid, where our R group is, that can change the acidity as well. So for acetic acid, the pKa we said here was around 4.76. If I add 1 chlorine, this is electronegative, it's going to draw electron density out. And so that's going to, via induction, make this more acidic. So my pKa now is 2.9. So that makes it more acidic. If I add 2 chlorines, that's going to have an even greater effect. My acid pKa now will be 1.3, and for 3 chlorines, my pKa is 0.9. So that hydrogen is just ready to fall off when we add all those extra chlorines, drawing electron density out. If I have a fluorine, which is even more electronegative than chlorine, just 1 fluorine, my pKa will be -2.3. And if we have a chlorine that is further away, so this is 2 carbons away, that does not have as great of an effect. The pKa is about 4.5. And then when it's closer, a little bit closer, but not as close as this one up here, this is 4.1. So the substituents matter. So electronegative substituents make it more acidic. If they're closer to the hydrogen or carboxylic acid, it has a greater effect. The electronegative atom matters, so fluorine versus chlorine. The closer the electronegative group is going to make it more acidic. And if you have more electronegative groups, so 3 chlorines versus 1 chlorine, that's going to make it more acidic. If we're looking at benzoic acid, the Y group, which is para to the carboxylic acid, is also going to affect the acidity. If we have these electron withdrawing groups, that's going to make it more acidic. So that is drawing out electron density, just like the halogens did on the last slide. And activating groups, electron donating, these ones are going to make them less acidic. So if we're going to put electron density into the ring, that's going to make it less acidic. So if we look at this one to figure out which one is the most acidic, I have water, which is not in the running with the rest of the carboxylic acids. This one is actually the least. The most one is going to have an electronegative atom. 2 of them have fluorine. If we add more electronegative fluorines, that's going to make it even more acidic. So this is the most. If I call this 4 and this one, this is 3. And 1 fluorine is better than 0. So this was 2. We already have a couple of ways of making carboxylic acids. The first is doing a benzylic oxidation. So we oxidize the benzylic hydrogen to give us benzoic acid. So then in this case we have a nitro group here. We can use the Jones reagent to do an oxidation. And this is drawn incorrectly. This should be an O here. So that gives us a carboxylic acid. And if we have an aldehyde using the same reagent, we also make a carboxylic acid. A new way to make carboxylic acids is actually using a nitrile. We've done the first reaction before. This is just an SN2 reaction where the nitrile is our nucleophile. So we have this negative here. This is my leaving group, electrophile. So we're going to do an SN2 reaction, and that is CN at the top there. And if we add sodium hydroxide and water followed by acid, it's going to hydrolyze the nitrile to give us the carboxylic acid. We're going to add a carbon in this step, and then we hydrolyze to the carboxylic acid. This reaction is best done with primary halides because elimination can occur with secondary or tertiary. We can also use a Grignard to make a carboxylic acid, and in this process, our nucleophile is the Grignard. This is my electrophile, carbon dioxide, so here is going to attack here. We typically add acid to this reaction, but I'll show you the intermediate. So if we add acid and water, we get a proton transfer to give us the carboxylic acid. So this reaction also adds a carbon, and then we form the carboxylic acid. So here we get benzoic acid. Cyanocycline, which is shown on the left, is isolated from the bacterium Streptomyces lavandula. This has antimicrobial as well as anti-tumor activities. So we can see that nitriles are important biologically. Some nitriles can be part of sugars. So here's one right here. This is lotolstrelin. This is isolated from the cassava plant and is a natural insecticide. Ways that we can make nitriles. So we've seen one way, which is the SN2 reaction using the primary alkyl halide, where this attacks here. And this is going to add a carbon in that CN step there. So we can draw it out also like this. And if we have an amide, we add thionyl chloride, which in other reactions we've seen it used to replace an OH with the Cl. Here it's going to act as a dehydrating reagent. It's going to remove the oxygen, this part of it, and form the nitrile. So that's the nitrile at form. So this is the carbon here, same carbon right there. Reactions that we can do with nitriles. One is the hydrolysis that we've seen. If you have a nitrile, you add a whole bunch of water, you form a carboxylic acid. So this carbon here is this one here. And if we do a reduction, so lithium aluminum hydride is our really strong reducing reagent, or this H-, that's going to reduce here. And we're going to get, instead of a primary alcohol like we did with esters and carboxylic acids, we're going to add a bunch of hydrogens and end up with a primary amine. We saw in the last chapter that we could react a Grignard with a nitrile, and this one kind of gives us a weird product that you might not expect. This is going to be our electrophile here, this carbon on the nitrile. The R is our nucleophile. So this will attack here. We have an R with that carbon. There's still an N here. Those electrons got kicked up, so this is N-. We then add H2O. So we see that in the second step, the H3O plus, and this will become a ketone. So a Grignard plus a nitrile equals ketone, and NH3 is a side product. So Grignard here with the nitrile, I'm going to add a carbon. This is this carbon. This will be the ketone that forms, and here's the carbon that got added. So there's 1, 2, this is 1, 2. So if we take a look at this problem, how would you prepare a compound from a nitrile? So we just saw that we could make a ketone using a nitrile. So we got to figure out what nitrile. This is the carbon that was the nitrile part. So you might start with this, and then we have 1, 2, 3. This is this one, so 1, 2, 3. No, 1, 2, 3. And the Grignard that I would need is going to have these 2 carbons, so it'll be ethyl magnesium Grignard, followed by water and acid.